Hello and welcome to Ask Echometer. My name is Carrie-Anne Taylor, and joining me today, Gustavo Fernandez, who runs the chat and Q&A. Also, Ken Skinner, Dieter Becker, Lynn Rowland, and Tony Podio. So today's session is titled Best Practices for Shooting Fluid Levels on Difficult Wells. And best practices under any circumstance should become methodical, intentional practices. If you've ever had the opportunity to go out in the field with our support technician, Ken Skinner, you know that Ken is extremely methodical from the moment he pulls up to a well until he pulls away. And it's because of this practiced method that he doesn't miss anything. He is excellent to learn from, and he is safe because he puts best practices ahead of time constraints, ahead of his cell phone ringing, ahead of any other distractions. So best practices start before you even install your gun on the well. So let's go ahead and review some of these. Number one, know the pressure on the well at the surface. The first thing you should do is check the well pressure. And number two, be alert that equipment ratings exceed the well pressure. I'm going to say it again, and you should say it with me. Be alert that the equipment ratings exceed well pressure. So we've got guns for different pressure ranges. If your well pressure exceeds the working pressure of the gun, do not install your gun on that well. If you install your gun on a well, close in the casing valve to start building up the pressure and then get distracted for any amount of time, go back to number one and check the pressure on the well at the surface. Then make sure that the equipment ratings exceed that wellhead pressure. If the pressure is built up too high and you're exceeding the equipment rating, close the valve between the gun and the well, open the casing valve back up to stop the pressure building up and make it safe. Maybe you can still acquire your data if you're fast, or maybe you just need a higher rated gas gun for that well. Number three, check the threads on the wellhead valve for corrosion, wear, or damage. So we recommend you have a wire brush or a rag that you can use to clean off the threads on the wellhead and make sure you'll be able to have a good, safe connection. Number four, for 2-inch NPT threads, make 4.5 turns for a safe connection to the wellhead. So make sure the threads on your gun are in good condition. Make sure you wrap the threads on your gun with Teflon tape. We have had people call in whose threads on their gun have been stripped or they didn't have a good connection. And when they opened up that valve between the gun and the well, the pressure blew the gun off the well because they did not have a clean, safe connection. So be safe. If conditions aren't safe, then don't shoot a fluid level on that well. Another recommendation is that you do not use any type of quick connect between the gun and the wellhead. So those connectors will not have the same pressure rating as your gun. If you're using any type of fitting between the gun and the wellhead, know the pressure rating on that fitting, and that has to be your maximum allowable pressure if that pressure rating is less than the working pressure that's engraved on your equipment. So again, be safe. If the conditions aren't safe, then maybe you shouldn't shoot a fluid level on that well. All right, number five. Close off other connections to the casing annulus. So this means isolate the path between the gun and the wellbore. If there are any other paths the pressure can take once you fire the gun, the result will be a very noisy fluid level shot. When the gas gun is fired, that released pressure wave wants to expand, and it will expand and move and echo through any paths that are available. So to minimize the noise, isolate the path between the gun and the well. And number six, charge the gas gun volume chamber above the estimated casing pressure. Now, this is especially true for the remote fire guns that are operated in explosion mode, meaning you'll use an external gas supply to fill the volume chamber. We talked about last week to minimize internal damage and maintenance on your remote fire gas guns. Make sure you have the gas gun charged with differential pressure over the wellhead pressure before you even open the valve between the gun and the well. If you're using one of the manually fired guns, the compact gas gun or the 5K gun, then you may be operating the gun in implosion mode, in which case you'll need to decide ahead of time if you'll be filling the gun with external pressure, like CO2 or nitrogen, for an explosion shot into the well, or if you'll be using the well gas to implode into the gun to create your shot. And we'll talk more about that differential pressure in just a bit. And then number 7, make sure the casing valve between the gas gun and the casing annulus is open before the shot is fired. All right, so let's talk a little bit about the effect of the gun connection. So here you see a 5K gun that's attached to this wellhead here. We see the compact gas gun that's 2-inch connection. Optimum results will be obtained when the gas gun is connected to a 1/2-inch or larger fully opening valve. So the 5K gun and the 15K gun both have a 1/2-inch connection. So anything smaller than that, and you're going to choke too much energy off the shot. Optimum results will be obtained when the gas gun is connected with the shortest possible distance between the gun and the casing. And we recommend that the gun be installed within 5 feet of the wellbore if possible. Once you fire the shot, if the pressure wave has to travel 8 to 10 feet around curves and through big pipe, skinny pipe, and valves, you'll see a lot more noise on your shot since you have that length of pipe acting like an echo chamber. Also, depending on the environment in the well, you'll need as much energy coming off that shot as possible, so a short direct line to the wellbore will provide your best shot. That being said, if 8 feet from the wellbore is your only option, then make sure the path is open, that you aren't shooting through multiple valves that will choke the shot. And you may need to increase your pressure differential so you'll have a better chance of getting more energy to the wellbore to get a good fluid level shot result. Adapters and pipe size reducers may be used if necessary, but they will result in a reduced signal amplitude. Shooting through a needle type valve can obstruct or block the signal, and it's not recommended, and we'll look at a couple of shots here in just a minute. And shooting through a chemical pot will cause a resonating signal and will give poor results. And we have a picture of one of those here in a minute as well. Okay, so let's talk about shooting through needle valves for just a minute. So this is a shot that was taken through a needle valve. So for those of you who are familiar with analyzing fluid level shots, especially when using the collar count method, you know the first 2 things you look for are a definite fluid level kick and a good collar count. And we think a good collar count is where the collar count marker is at least 75 to 80% of the way to the liquid level. But a needle valve, when you shoot through it, chokes the energy coming off of that shot. So the remaining energy that gets past the needle valve and into the well is much less. So as a result, the pressure differential is not as strong. The shot is noisy. The software is unable to identify collars for a good collar count. So we see all this noise right here. We see the collar count marker right here. So a poor collar count means that your analysis is going to result in an acoustic velocity calculation that's not representative of what the acoustic velocity is at the fluid level depth. So an inaccurate acoustic velocity results in an inaccurate fluid level depth calculation. So looking at this shot, the collar count is only about 30% of the way down. This means the software was able to count collars to about 1.7 seconds, but there's still about 4 seconds of time from the collar count to the liquid level. So to account for that time, the software calculates the acoustic velocity at that last collar it was able to identify. So here the calculated acoustic velocity is 1,163 feet per second. Now the software uses that acoustic velocity and the time remaining to calculate the number of joints there would be along that distance. Then it takes that calculated number of joints and adds them to the actual number of joints counted. And then multiplying that by the average joint length in the well file, that calculates your fluid level depth. So the resulting fluid level depth here is 3,397 feet. So the problem here is that typically on a producing well, as the depth of the wellbore increases, the pressure and temperature are increasing, which means the acoustic velocity increases. So let's look at a comparison shot to help us understand what that means in terms of accuracy. So in this comparison shot, the needle valve was removed. and a second fluid level shot was taken. You can see that the noise level is much lower. We see a more sharp and precise fluid level shot, and we see the collar count is almost all the way down to the liquid level. So now the software only has to account for about a quarter of a second of time, right? This little bit of time right here. So the acoustic velocity calculated is 1,278 feet per second, and the fluid level depth calculation is more accurate, 3,636 feet. So that's a difference of about 240 feet. Now, the accuracy you're looking for may depend on the question you're trying to answer, but we want to make sure you have the tools you need to get the most accurate fluid level response and the most accurate fluid level depth calculation. So shooting through a needle type valve can obstruct or block the signal, and it's not recommended. So this is the beginning of a shot that was taken through a needle valve. So if you see a response like this, when the shot is fired, where you can tell this energy has been cut off, it's an indication that something is choking off the energy coming off of your shot. It could be a needle valve, it could be grease or something right there where you've got the gun hooked up, but something is choking the energy off the shot, and this indicates you need to make a change so you can have more energy entering the wellbore to get better fluid level shot results. So this is a picture of the well that we do most of our testing on. This is the V11 well. And one day, Ken went out to the well, and the lease operator had installed this chemical pot that you see here. So if you were to install your gun onto this apparatus and shoot a fluid level, it's unlikely much energy would make it out of the chamber pot and around the corner and down the wellbore. So it acts like a big muffler. So we asked that a T be installed so we could isolate the path between the gun and the well and close off the connection to that chemical pot to avoid that sort of echo chamber. So this is a simple illustration demonstrating the best shot is to have your gun installed as close to the wellbore as possible. If you have 1 or 2 L's you have to shoot through, that's okay. It may reduce some of the energy coming off the shot. Shooting through a reducer of some kind will choke some energy. But even through all of that, if you can at least get your gun within 5 feet of the wellbore, that's your best chance at getting the most energy from the gun to the wellbore. Before we move on from installing the equipment, a question that we get asked fairly often is, which type of gas is better to use for charge pressure in the gun? So let's look at some of these differences. First of all, the gun doesn't care which type of gas you charge it with. It's going to create the same shot either way. The difference lies in the amount of pressure that you need and the temperature you're working in. So a 5-pound CO2 bottle will provide a lot of shots depending on the charge pressure that you're using. And I've included this chart from an Excel spreadsheet. It shows the number of shots you could get out of a 5-pound CO2 bottle based on the outside temperature, and assuming you're filling the gas gun to the maximum vapor pressure of CO2. All right, so if you download the PDF documentation bundle from the Ask Echometer website, it's session 14, then this is included with that information. You can fill your CO2 bottle from a siphon type bottle, and Ken has created instructions to fill both CO2 and nitrogen bottles, and I've included both of those in that session 14 PDF bundle as well. The CO2 critical temperature is 88 degrees Fahrenheit and 1070 psia. So if the bottle contains liquid, the CO2 pressure is 650 psi at 50 degrees, 300 psi at 0 degrees Fahrenheit, and 120 psi at minus 50 degrees Fahrenheit. So if you have a well pressure of 600 psi and it's December and it's 15 degrees outside and all you have is a remote fire gun and a CO2 bottle, you can't shoot fluid levels on those wells. As long as the temperature of the CO2 gas is high enough that the vapor pressure exceeds the well pressure, CO2 is going to be the most convenient gas to use for acoustic testing. But if the well pressure exceeds that vapor pressure of the CO2, nitrogen gas is going to be your most common gas to use for acoustic testing. So if you're in colder weather or if there's a need for higher pressure differentials, nitrogen gas is typically used. If you use nitrogen gas when you purchase your equipment from us, you also have the option to purchase a pressure regulator to make sure that you're remaining within the working limitations of your gun. All right, so just a few safety reminders before we move on. Number one, bleed off the well pressure before removing your gas gun from the well. Keep your threads clean and in good shape. Last week's session was all about care and maintenance of your equipment. So if you have any questions on cleaning your equipment or which products to use or some of the resources that we have available, please take a look at last week's session. It was titled Equipment Maintenance and Troubleshooting. So it's session 13. And so you've got the video you can watch and then all of those resources that you're able to download. Just moving on, number 3, do not exceed the working pressure of the gun. Make sure you know which type of gun you have, and the working pressure is engraved on the side of the gun. Make sure the gun is securely attached to the well, and make sure the casing valve is open before firing the gun. With the older style guns and the older microphones, you would have run a chance if you fired the shot and you didn't open that valve between the gun and the well of cracking the microphone. There's little piezoelectric crystals in there. The microphones are pretty rugged now, so it probably wouldn't do much damage, but you'd still have to recharge the gun and open the valve and retake your shot there. All right, background noise. So you've got the equipment hooked up and now you're ready to take your shot. You want to make sure you've done what you can to eliminate or at least minimize the background noise on your shot trace. One way to see possible background noise before you've even taken your shot is to look at the trace on the screen once you've opened the valve between the gun and the well. And I'm talking about this little bit of the shot trace that you see here before the shot was fired. Before you start acquiring or press that take shot button, you can see the noise level going across the screen there. You can see it across the display. So you can identify excessive downhole noise. If you have a really gassy well, there's likely going to be a lot of noise. If it's significant, you'll see a message pop up from the software recommending a larger charge on the gas gun to help overcome the downhole noise. You can also identify mechanical noise, like noise from the pumping unit. Mechanical noise is rhythmic, coinciding with the strokes per minute or some other machine with repetitive operation. So you can go ahead and identify that beforehand. We always teach that you should always shoot your fluid levels with your units running, because once you shut down your well, you start changing conditions. And so one of the main reasons to shoot a fluid level is to learn where the fluid level is at under normal operating conditions. So a lot of background noise can be filtered out after the shot is taken by using the low-pass filter. But if the mechanical noise is significant and interfering with your analysis, you may need to shut down the unit to shoot the fluid level. So aside from mechanical noise, downhole background noise on the trace, or when you shoot your fluid level, you have a noisy shot with a bad collar count, try increasing the pressure in the volume chamber and retake that shot. And remember, we want you to take at least 2 shots for comparison anyway. Some of you work with deep, low-pressure wells. If increasing the pressure differential doesn't help, then additional wellhead pressure can also help improve your collar count and your liquid level response. I always think you've heard people say in space, no one can hear you scream. That's because there's no pressure medium for the sound to travel through. So it's the same thing in a well with really low pressure wells on vacuum. And they can often be the more difficult wells to shoot fluid levels on. So we have some tools for those deep, low pressure wells or wells on a vacuum. In addition to increasing the chamber pressure and increasing the well pressure, we also have a larger volume chamber. So here you see the remote fire gas gun, which has a volume chamber of 12.5 cubic inches. And next to that, you see the larger 32 cubic inch volume chamber. And the idea behind the larger volume chamber is that you have a larger volume of gas that you're shooting down the wellbore and a better chance of getting the pressure wave to reach further down. So in this smaller picture, you see a comparison of charge pressures. You see the 100 psi, the darker blue. Here we see 350 psi, and then the largest reflection kick you see here is 900 psi charge. So if you'll see, this well here has a casing pressure of minus 1.5 psi. And here you see the 3 fluid level shots using the standard volume chamber on the gas gun. So we see 300 psi, this green trace. The light blue trace is 500 psi. And the dark blue trace is 900 psi. Then in the black trace here, we see the larger volume chamber being used with the 900 psi pressure differential on that volume chamber. So you can see that there's a much bigger response. So lots of times that larger volume chamber is going to allow you to get a little bit better shot. You all are likely familiar with the low pass filter that filters out background noise. And so low pass indicates only the lower frequencies are allowed to pass through, which makes it easier to see the low frequency fluid level kicks. But in wells on vacuum, sometimes it helps to allow more of those higher frequencies to pass through. It helps provide more detail. High pass filters are what the software uses to count callers. So a tool that we've added into the software to help with finding the fluid level on wells on a vacuum is a high pass filter. And it's located in the fine tune button in the software. It's the same place where the low pass filter is located. So in this shot comparison, you see the original shot as it was received, and then below it, the same shot with the high pass filter turned on. So you can see the increased noise levels and the detail of the response. And then here's an analysis comparison of the fluid level shot, and then below it, the same shot with the low pass filter turned on. All right, so the low pass filter removes those high frequency noise spikes. So this is the same shot here with the low pass filter, same shot with the high pass filter. Now, if you're just analyzing a regular fluid level shot, turning on the high pass filter is probably not going to help you. We've seen where it can reverse the polarity, can cause you probably some confusion. So just use the high pass filter with caution. It was created to use for wells on vacuum. Of course, that low pass filter does a wonderful job of helping to eliminate a lot of the background noise. All right, so for those of you who keep your well analyzers plugged in while you're acquiring data, you may sometimes see the noise from the electronics show up on the shot. If it gets in the way of your analysis, you may need to unplug the well analyzer to shoot the fluid level. And so that's one good reason why it's important to have a healthy 12-volt lead acid battery in your well analyzer to be able to operate the system on battery power. So direction of kick, and this is, again, kind of getting back to the basics, but the direction of kick is an essential part of making sure you understand the fluid level shot you acquired. A downward kick indicates an obstruction or something taking up room, like the fluid level, or a decrease in cross-sectional area, like a tubing anchor. An upward kick indicates an increase in area, like a perforation into the tubing or a hole in the tubing. So the up kicks or down kicks you see on your fluid level shot should coincide with the physical characteristics of your wellbore. So it's always a good idea to have with you, or at least have access to, the wellbore schematic for the wells that you're shooting. So the direction of kick of the liquid level is the same direction or the same polarity of the pulse generated by the gas gun shot. So a downward kick when the shot goes off means you're looking for a downward kick at the fluid level. The software will assume you're operating your gun in explosion mode unless you tell it otherwise. So if you're using your gun in the implosion mode, if you're imploding shots, you need to let the software know. Otherwise, the polarity will be reversed and you'll see an up kick rather than a down kick for the fluid level. So just a quick reminder there. So continuing on with the direction of kick, this is a simple illustration and a fluid level shot of a well with a tubing anchor located just before the liquid level. Typically, we always say that you can't see past the fluid level on a fluid level shot. So when you see kicks beyond the fluid level, you need to be able to identify those. And in this particular shot here, we don't see that as much, but there are some shots you may take where the tubing anchor is a little bit higher up in the wellbore before you hit the liquid level. And you may see another downward kick after that liquid level. So what's happening, if you can just visualize how that pressure wave is moving through the wellbore, that pressure wave is coming off the gun, it's traveling down the wellbore. It hits the tubing anchor, so we see a down kick off the tubing anchor. Now we hit the fluid level, so we see our big down kick off the fluid level. Now that pressure wave is traveling back up out of the wellbore. So when it crosses anything in its way back up, we're going to see a reflection off of that. So here you might see a downward kick off the tubing anchor, downward kick from the fluid level, and then another downward kick as that pressure wave is traveling back up out of the wellbore. On this particular shot, the tubing anchor was so close to the liquid level that kick off the fluid level just sort of overcame any any chance that you would be able to see that kick off the tubing anchor. But liners are a little bit different, and they can cause some confusion if you aren't aware of the reflection kicks that they create. So here we see a fluid level shot on a well with a liner. The shot goes off, that pressure wave is traveling down the well bore. We see a kick off the liner. We see a kick off the liquid level. Now that pressure wave is traveling back up out of the well bore, and when it gets to the top of the liner, there's an increase in area when it crosses that top of liner. So we see an upkick as that pressure wave is traveling back up out of the well bore. So sometimes the liner kick is the largest downward kick. And so you have to make sure that you're not allowing the software, first of all, to pick that as your liquid level. So you always want to be aware when you have a liner in the well. If you're shooting down the tubing or down a pipe with no collars that can be counted, or you don't have anything that you can use for a downhole marker, now you have to use the acoustic velocity and the time from the shot to the liquid level to calculate that liquid level depth. So the distance to the fluid level is calculated by taking the time to the liquid level, multiply that by the acoustic velocity, and now we divide that by 2 because we're talking about round trip travel time, but we're only wanting the distance one way. We're wanting the distance from the surface to that liquid level. All right, so that's why we divide that by 2. So in this example, if the time to the fluid level is 19 seconds, the acoustic velocity is 1,120 feet per second. We'll multiply the time times the acoustic velocity, divide that by 2, and so that gives us our fluid level depth of 10,640 feet. So you need to make sure that you have an accurate acoustic velocity. So let's talk about the acoustic velocity for a minute. The acoustic velocity is a property of the gas you're shooting the pressure wave through, right? So the gas you're producing in the well. The gas has a certain gas gravity, and these charts you see here are the acoustic velocity charts for these 2 gas gravity types. And the acoustic velocity of these gases depends on the pressure and the temperature in the well. So it's really important that you're aware of the acoustic velocity range that you should expect to see on every single fluid level shot you take on every well that you go to. And so you're able to create your library of shots on that particular well. And so you have those previous shots to refer back to if you need to. But one of the things that we suggest, it's an excellent quality check, is for you to know the acoustic velocity on your wells. So here's an example. This is a gas gravity of 0.6. So this is a lighter gas, probably say like methane. So here we have the gas gravity of 0.6. Along the bottom here, increasing to the right, you see the pressure. Pressure is increasing here. Each one of these curves that you see within the graph represent a temperature curve. And then increasing along the left-hand side, you see the acoustic velocity in feet per second. So if we had methane gas, or gas gravity of 0.6, and the pressure in the wellbore is 400 psi, and the temperature is 108 degrees Fahrenheit, well, we come across on the chart till we hit 400 psi. We move up the chart until we hit the curve that coincides with the temperature in the well. Move across to the left, and we see that the acoustic velocity for this gas under these conditions is 1,400 feet per second. Now, if you have a heavier gas, so this is a gas gravity of 1.2, closer to, say, propane or butane. Under those same conditions, if we come over here to 400 psi, and we start moving up until we hit the temperature curve that coincides with 108 degrees Fahrenheit, and we move over to the left, we see that the acoustic velocity for this particular gas is 785 feet per second. So it's important that you know, it's imperative that you know the gas gravity in your wells, or at least the types of gases, the types of gas that you have in the well. If you have a gas composition or a gas sample, you can enter that information into the software and it will calculate a gas gravity for you. And so it's important that you know the type of gas and then the average pressure and temperature in the well. If you're just guessing on your gas gravity, you're basically guessing on your fluid level depth, and because you can see here how much of a difference it makes, depending on the type of gas that you have in the well. All right, so another difficult well to shoot fluid levels on is a well with a high fluid level, where the fluid's up near the surface. One of the characteristics of a high fluid level is this funnel shape at the beginning of the shot, and you see it just tapers out. Now, if the fluid level falls within the first 1.5 seconds of the shot being fired, the software is not going to see it, and that is by design. So that means you're going to have to zoom in to the beginning of the shot and move that liquid level to the correct location. If you've just taken a big shot with a large pressure differential and your fluid level is near the surface, it may be difficult to see where that fluid level is at because of all of the energy coming off the gun when the shot is fired. The amplitude just overcomes any chance of being able to see where that liquid level is at. So in this case, you need to decrease the pressure differential in the volume chamber down to maybe 50 psi over the well pressure and retake the shot. You're not worried about seeing deep into the well. You only want to see what is right there at the surface. So a smaller pressure differential is going to give you more detail in this case. Also, if you'll notice, the software placed the fluid level marker right here at 8.5 seconds. This is a default placement location when the software doesn't know where the fluid level is at, when it doesn't know what to do. Sometimes the software will notify you that it couldn't find the liquid level, and it will place the marker near the beginning of the shot. Sometimes it's going to place it right there at 8.5 seconds. So if you have a high fluid level like we see here, or maybe you have a well with multiple kicks and noise and no definite liquid level marker location for the software to choose, if you see the liquid level marker at 8.5 seconds, always first assume the software didn't know what to do. Maybe it actually is where the fluid level is at, but always double check it. If you're not sure, then maybe you need to adjust your pressure differential on your gun and then start retaking shots until it makes sense. So this is a foam well. We see these wells occasionally, shots off these wells. The foam here refers to a foam column in the well consisting of about 400 feet of small gas bubbles surrounded by oil. So the gas bubbles are less than 1/10 of an inch in diameter. They're tiny bubbles. They're not moving, so a thick, still column of foam. Foam wells are quiet. They have negligible downhole noise. When you try to shoot a fluid level on these wells, you have a weak liquid level response. The foam just absorbs that shot rather than reflecting it. The foam columns are less than 400 feet high. If the column gets taller than that, then the bubbles start collapsing in from the weight. Also, there's no gas venting from the casing. It's just a still, quiet, foamy well. So to shoot these wells, you'll need to use a large charge on the gas gun or use the larger volume chamber if you need to. So if the depth to the liquid level is not obvious, what can you do? So let's say you've taken your multiple shots with no repeatability. You have multiple downhole reflection kicks on the shot trace and nothing stands out as a liquid level. Maybe the liquid level is below the liquid entry point. You're getting a reflection kick off the liquid coming in from the perforations, but the fluid coming in is obstructing or preventing you from seeing below that liquid entry kick. Or maybe the liquid level is below some type of partial annulus obstruction. But when the liquid level isn't obvious, then one thing you can do is move the liquid level. Now is when you want to start changing conditions in the well so that you can see where that liquid level is at. So the liquid level can be raised by shutting down a producing well, or it can be depressed or pushed down by increasing the casing pressure if casing gas is produced. One of the nice things about the TAM software is that you can easily overlay shots. So the multiple shots that you've taken can be overlaid and compared. When you close the casing valve, you're taking multiple shots, that pressure is building up in the casing annulus. And you can see that from shot to shot. You'll see that pressure increase from shot to shot, even if it's slight. But while that pressure has been building, depending on the annular gas flow rate, the fluid is likely being depressed. Everything that is stationary, that is physical in the well, is going to remain at the same time on every single shot. And so the only thing that you're going to see move is the liquid level. So if the liquid level is high and casing gas is available, increasing the casing pressure will depress that liquid level. And there's a general equation that you can use here. 1 psi is approximately equal to 3 feet of oil. So in this illustration here, if you start out with 50 psi on the casing, you shut the well in, increase the casing pressure to 150 psi, then a 100 psi increase would move the liquid level down approximately 300 feet. If your liquid level is already near the end of the tubing and the casing pressure is building up quickly, if you wait too long, you might see an upkick at the liquid level rather than the down kick you were expecting. That just means you've pushed the liquid level down below the end of the tubing. So this shot here is a very typical shot of the liquid level just below the end of the tubing. You see a big upkick from the increase in area past the end of the tubing, and the liquid level is the downward part of that kick immediately after. It looks like this big up-down kick. So here's an example where the liquid level was proven by moving it with increased casing pressure. This window you see you probably recognize as the pressure buildup window that you see when you shoot your fluid level and get your 2-minute pressure buildup. You can continue to build up and record pressure on a regular fluid level shot for up to 15 minutes. This pressure was recorded for 7 minutes, and then the shot was taken again. So shot number 1, the casing pressure was 3.5 psi. Shot number 2, the pressure's been building for several minutes, and the casing pressure is now 7.9 psi. This particular well had a saltwater gradient of about 0.5 psi per foot, which equates to about 2 feet of change for every 1 pound of pressure change. So depending on all of the factors involved, the gradient, the flow rate, the casing size, increasing the pressure 4.4 psi would equate to a movement of approximately 8.8 feet. So with the shot comparison, we see that increasing the casing pressure depressed that gassy liquid. Everything that was stationary in the well remained the same, and only the liquid level changed. If the liquid level is at the pump or casing gas is not available, you can stop pumping the well. The noise settles, and as the liquid enters the wellbore, liquid level is starting to change. So this is a fill-up rate chart. You see the chart of the pipe sizes right here, the annular capacity in barrels per 1,000 feet, and then the annular area. Along the bottom is the production rate in barrels per day, and up the side is the fill-up rate in feet per minute. So you had a production rate of 95 barrels per day with a pipe size of 2.5 and 4.5. Your fill-up rate would be 8 feet per minute. So a situation you may use this if you had a well where your liquid level was below your liquid entry point. Maybe your liquid level is down below your perforations and you've got fluid coming in. When you shoot that fluid level, all you're seeing is the fluid coming out of those perforations, but you know that your fluid level depth is down below the perforations. So if you shut off the well and say you start shooting fluid levels about every 15 minutes, you're looking for a change in that fluid level. You're looking for the fluid to come up above that fluid entry point. And so maybe after 45 minutes, you finally see the liquid level kick above that liquid entry point. Now you can use your fill-up rate chart to determine that if the well was stopped for 45 minutes and the fill-up rate is 8 feet per minute, then the liquid moved 45 minutes times 8 feet per minute, or 360 feet. So you can add 360 feet to that last liquid level shot where you saw the liquid, and that will give you an approximate location of where the liquid is at under normal operating conditions. You know, it sounds a little tedious, but it's a tool that you can use if you're in a bind and needing to get some information. Slim hole, low pressure. So the problem you're facing here is that the tubing size is only slightly smaller than the casing size. So each collar reflects a high percentage of the signal back to the surface. Only a very weak signal reaches the bottom of the well and reflects off the liquid. So if you encounter this situation, you want to reduce the well noise, increase the pressure in the wellbore. Sometimes even a 5 psi increase helps carry the pressure wave down the annulus, and use a larger pressure differential on the gun. So we're all likely familiar with wells with an annular gaseous column. A gaseous column is defined as an oil column which is lighted or lifted by rising bubbles. The problem encountered here is that the rising bubbles lighten that oil column, which makes it difficult to calculate an accurate producing bottom hole pressure. You guys know these characteristics probably as well as me, or better. Characteristics of a gaseous column include gas venting from the casing annulus, which sometimes causes erratic liquid levels. There's considerable downhole noise, and you see an increase in casing pressure when the casing valves are closed in. So just before you shoot a fluid level, you close the casing valve to the flow line. When you take your shot, the software begins to record pressure data, 1 data point of pressure every 5 seconds. That's what TAM records. We recommend a 2-minute pressure buildup per shot. And the reason that buildup is important is because the software uses that buildup rate in your annular area to calculate a gas flow rate. Then it uses the gas flow rate to determine the percent liquid in that gaseous liquid column. And then it mathematically separates the gas and liquid to determine an accurate producing bottom hole pressure. And I've included a technical paper in that Session 14 PDF bundle download that discusses the gaseous column correction factor that we use, just in case you're interested in understanding a bit more about that. And you're always welcome to email us or call us if you have questions. All right, so this next example is a great example of how changing conditions in a well can help you analyze your shot if something doesn't make sense. When we're asked how many fluid level shots you should take on a well, our response is to keep shooting fluid levels until it makes sense. And as we've talked about, that might include changing the well conditions. So here we see a fluid level shot. This particular operator shot this fluid level, and he saw this downward kick on the shot trace, and here he sees his liquid level. So he looked on his wellbore schematic, and there was nothing to indicate that anything should be in the wellbore taking up space at the point at this 4,005 feet where he saw this downward kick. So he gave us a call, and we suggested that he change the conditions in the well. We told him to stop pumping the unit. So when he stopped pumping the unit, he allowed it to settle. He shot another fluid level, and now he sees an upkick at that exact same location where he saw the down kick previously. So what was happening was, as the well was pumping, the fluid was coming up the tubing and out the hole. So when he shot the fluid level was reflecting off the fluid coming out of the hole in the tubing. When he turned the unit off and allowed that to settle for just a minute, now there's no fluid coming out of the hole, so we see the upkick from the hole in the tubing there. We have this shot we can look at here in just a bit. So if you're able to take a dynamometer measurement at the same time, then your downhole card can also provide information. This is the downhole card for the shot we just saw with the hole in the tubing. The pump card displays abnormal loads due to lifting liquid up and out the hole rather than lifting the fluid load all the way up to the surface. So this is very characteristic of a hole in the tubing. The pump card shape indicates a full pump load, but we would expect the top of the full pump card to reach the maximum load line. So this is very characteristic downhole pump card of a hole in the tubing. All right, on this next example, we see 3 up kicks and a large down kick where the software labels the liquid level. This is a coal bed methane well with 3 sets of perforations and the pump set below the perforations. So we can enter those perforated intervals into TAM and then turn on the wellbore overlay that we see here. So we see the perforations here lining up nicely with our up kicks. With these large kicks across the perforations, it may be difficult to get a good color count, but we can definitely use these up kicks as downhole markers and get really close to the liquid level for our depth determination analysis. So when you're determining which method you want to use to calculate your fluid level depth, when you click on method 2, the downhole markers button, anything that was entered into the well file that can be identified by a reflection kick is displayed as an option to use for the downhole marker. So we can easily make our way down the visible kicks. We can match them to the information from the wellbore schematic. And now we have a good shot analysis and an accurate distance to the liquid level. Once you click that downhole marker button, then you see the perforations options come up. And so you can kind of work your way down perforation 1, 2. There's the 3rd perforation, and it's closest to the liquid level. So that would be a very good downhole marker to use for an accurate liquid level depth calculation. All right, so using the 3rd set of perforations here, this 3rd upkick, the calculated fluid level depth is 1,887 feet. So this is the depth determination screen for those downhole markers. You see the downhole marker options available to choose from across the top. The closer you can get to the liquid level marker, the more accurate your shot calculation will be. On this example, choosing the last up kick, that third up kick gave us a liquid level depth of 1,887 feet. Choosing the second up kick here gives us a liquid level depth of 1,881 feet. So not a big difference here. This is a pretty shallow well, but some deeper wells with higher temperature changes and higher pressure changes, it's going to make a significant difference. The other option you have for determining the liquid level depth is to use the collar count method. On this coal bed methane well, the collar count was actually pretty good. The software was able to count collars down to that third perforated interval, and the resulting liquid level depth calculated is 1,879 feet. So we have a difference of 8 feet between using the collar count method and the downhole marker method. And maybe you're okay with an 8-foot difference, or maybe you're going to email us and ask us why there's a difference. So what is that difference? Both methods rely on information that you enter into the wellbore. The downhole marker method is using the depth you input from your wellbore schematic, which is dependent upon the measuring device used when the wellbore schematic was created. The collar count method is using the average joint length that is input into the well file. If you don't change that number, the default is 31.7 feet per joint. So there's two different methods relying on different well file inputs. And so if you'll notice here, the average joint length on this particular well was 32.61 feet. If it had been left at 31.7 feet as the average joint length, then that would have caused an error. You would have had an inaccurate fluid level calculation. So the average joint length is just as important in your well file information. So the default is 31.7. Unless you change it, that's the number that the software is going to use when it's calculating your liquid level depths. Okay, so let's talk about gas lift. This gas lift shot down the casing has a pretty good collar count, but a lot of times, and I'm sure you've seen, the collar count isn't very deep because of all the reflections coming off of the mandrels, all the repeats. It will add a lot of noise to the shot trace, and it makes the collar count and the gas lift mandrel selection really difficult. So we can first apply the low pass filter to clean up some of that noise. And so now we see the kicks coming off of the mandrels down the casing. In the TAM software, you can enter the gas lift valve depths into the well file under that lift system tab. And so now when we turn on the wellbore overlay, the reflection kicks off the mandrels are lining up nicely with that overlay, which makes it a lot easier to identify the kick that's closest to the liquid level. And I have a really good example of stepping through a gas lift analysis that we'll look at here in just a bit. So every time we teach a class where we talk about fluid levels, we bring up the acoustic velocity several times because we want you to understand its importance when you're analyzing a shot. So know the acoustic velocity you should expect to see on your wells. The acoustic velocity calculation, when you look at your fluid level shot, is just below and to the right of the distance to the liquid display. So it's right there. When you look at your liquid level depth, take a glance at that acoustic velocity. Look at that calculated value and make sure what you see is within the reasonable range you would expect for that well. It's an excellent quality check on your shot analysis, and it will help you make sense of your shots. And I'll put up a gas lift shot when we get to the examples and show you how the acoustic velocity can also help you in your downhole marker selection when you have multiple gas lift valves and it's difficult to choose the reflection that goes with that marker, if you've got 15 valves downhole. So we'll talk about this again when we look at some data. Okay, so here's a well with multiple kicks. That could be a very confusing shot to analyze. When we turn on the wellbore overlay, we see that in this well there is a tubing anchor, a liner, an end of the tubing, and then perforations. So what I do when I am analyzing a shot with multiple kicks is I start at the first marker I can identify. So here's the down kick at the tubing anchor. The next reflection we see down is down kick at the liner. Now the next possible marker is the end of the tubing, but I know that the end of the tubing would create an up kick, but I see a nice big down kick here. So I do believe this to be my liquid level, but there are kicks past the down kick. I see an up kick, followed by a smaller down kick. So this is where you need to look at the time intervals to help you out. So the time interval from the down kick at the liner top to the down kick at the liquid level is the same as the down kick from the liquid level to the up kick. So in the annotations button, when you're looking at your fluid level data, click on the annotations button and you can click on the depth reference line. And I use this line all the time. It's an excellent resource to have, and it will help you. It has the time, and then it also has the depth. The time interval calculations can help make sense of a lot of repeats, and it can help you discount reflections or discount kicks that are repeats so that you can concentrate on the reflections when you're looking at something physically in the well that you need to identify next. All right, so the time intervals help me identify that this is the up kick as that pressure wave is traveling back out of the liner. That following down kick is followed by smaller and smaller kicks at that same time interval, so we can identify these as the reflection bouncing back and forth between the liner and the liquid level. Okay, so which down kick is the liquid level? We see the software identified the liquid level as the largest downward kick, and that is one of the conditions that the software looks for. But we see some kicks before and after that liquid level, so we need to verify what we're looking at. When we turn on the wellbore overlay, we see there's a down kick at the tubing anchor, a down kick at the liner. So there's our tubing anchor, there's our liner. And then here we actually see a kick off the top of the gas separator. Now we see a nice big up kick at the end of the tubing, and then now we reach the liquid level. So shots can get messy when there's multiple reflections from a crowded downhole schematic, but if you just start from the top and work your way down, the tools in the software will help you step through the reflections to verify that your liquid level is correct. We've seen a few shots where the liner can create some confusion. So what if we have multiple liners in the well? So let's take a look at this example. First, we're seeing a lot of noise on this shot, so we'll apply the low pass filter to clean up some of the noise. So it looks like the collar count is right on top of what the software picked as our liquid level. But we're seeing a lot of kicks, so let's turn on the wellbore overlay and take a second look. All right, so we're seeing multiple liners here. So let's not panic, let's just work our way down. So we're good with the top of the liner here. And this possible liquid level kick is not anywhere close to that next liner top. And just past the liquid level, there's an up kick. We can look at the time interval from the liner top to the liquid level and from the liquid level to the up kick and the kicks past that, and verify that this is a reflection bouncing back and forth between the liner top and the liquid level. So what's this large kick at just under 18 seconds? Well, if we look at the time to the liquid level, which is about 10.3 seconds, all right, so our time to the liquid level, 10.3 seconds, and add to that the time from the shot to the top of the liner, which is about 7.5 seconds, that totals 17.8 seconds. So this large kick is the reflection of the liner top repeating off the liquid level. And you see this whole series of kicks repeated here. So we know to shoot a fluid level to find a hole in the tubing, and many of you with gas wells likely already shoot down both the tubing and casing to troubleshoot your wells. But there was some research done on troubleshooting rod pumped wells by shooting down the tubing. So we went ahead and threw this in here. If you would like more information on that, I've also included this technical paper in the Session 14 downloads, and you can also contact us. It was Lynn Rowland who did the research and worked with the operator on this paper. And so it's a great resource to have, and if you have any questions on that, please pass those along. All right, so wrapping up here, a few general liquid level comments. Recommended practice is to always acquire at least 2 acoustic fluid level shots. And if 2 shots isn't enough, then we want you to keep shooting fluid levels, and possibly you need to start changing the conditions until that fluid level shot makes sense. You're able to identify that liquid level. Don't forget that you can also take a dynamometer measurement. Your dynamometer measurement should complement your fluid level shots. So that can be really helpful when you're troubleshooting a well. Using the gas composition is often the least accurate depth determination analysis method, and so that is the acoustic velocity. So if you have a gas composition or a gas sample, if that's the only means that you have of getting an accurate acoustic velocity, then use that. But you also have your previous shots that you can look at to help you determine the average acoustic velocity so that you'll have a number to use when you're analyzing that fluid level shot. All right, so for an accurate liquid level depth determination, use an accurate and representative wellbore schematic. The deeper the marker, the more accurate the liquid level depth is going to be. Verify the correct reflection on the acoustic trace is selected to represent the downhole marker that you've selected, meaning as you're working your way down, if you've chosen a reflection that is not the correct reflection to use for a marker, that's going to make your acoustic velocity off. All right, so you want to make sure that you're aware of the acoustic velocity, and I'll show you a trick that you can use, especially on gas lift shots, and so we'll take a look at that here in just a minute. At 1,400 feet per second acoustic velocity, a 1/10 second difference in marker selection can make a 70-foot difference. As a quality check, always verify the calculated acoustic velocity is within the known range that you would expect. If there is ever a question between using the collar count or downhole marker, use whichever is closest to the liquid level. If you're using the collar count method, make sure the average joint length is correct. Do not shoot through a needle valve. Always connect the gun close to the casing, and do not shoot through chemical pods. All right, so that takes us to the end of the presentation here. And so I'll turn it over to Gustavo now to start addressing some questions.
Yes, thank you, Carrie-Anne. Yes, we've got quite a few interesting questions here. Let me start with Kenneth Spreading the Voice asking for a low-pass filter. So he's asking, can you explain what the low-pass filter is actually doing? What is it filtering out? Does it change the distance to the liquid level? And we see a lot of people always using the low-pass filter. Just tell us a little bit about this, Paul.
This is Lynn. I'll talk about it, and if anybody else adds anything in, it's welcome. But the low-pass filter has about 101 points in it, so that means we sampled 1,000 samples per second, so 100 points is about 1/10 of a second. So what the low-pass filter sort of does is it averages every running 1/10 of a second, and so it makes everything at 1/10 of a second kind of flatten out because it used 100 points to determine what the value is. So if you just imagine going through your acoustic signal and taking 100 points and dividing the points by 100, the amplitude, the height of the acoustic signal, that it's just going to basically smooth it out. And anything that's wider than 1/10 of a second will still show up. Anything that's narrower than 1/10 of a second will tend to disappear. And that's a kind of a quick idea of the low pass filter.
Thank you, Lynn. Travis is asking, is there a physical reason why the downward kick is an obstruction, or is it just defined like that?
It's kind of defined like that because the microphone output is the change in pressure. And so if you were to imagine a pressure wave that you shoot from an explosion shot in a well, then that's a increase, that's a hill of pressure. So it's a hill of pressure that is increasing to the peak and then decreasing after the peak. And so the change in pressure is a increasing slope to the peak and a decreasing slope after the peak. Well, that means if you plot the derivative or the slope of the pressure hill, it should go up and then go down. By convention, we've always plotted it inverse of that, so that a explosion shot represents a decrease in the wellbore and is plotted down. A increase in the wellbore is plotted up, and that's just by convention. It's really If we plotted it based on the derivative, it would be plotted differently.
Okay, and Hugo is asking if is it necessary to adjust the sound velocity in the gas by taking into account the temperature gradient too. And I'm assuming he's talking about that correction or adjustment when analyzing the liquid level for an acoustic velocity method using the gas gravity.
Well, anytime you use gas gravity, you need to put in the bottom temperature of the well, because the acoustic velocity is based on the average temperature. And so in the TAM software and TM software, Equimeter defaults the bottom temperature to be 150, and if you're in a deep well and the bottom temperature is 300 and you put in a gas gravity, then it's going to calculate the acoustic velocity based on 100 degrees as the bottom temperature. And so you need to make sure that you put in the correct bottom temperature. So if you use acoustic velocity method, then the correct temperature will be used to calculate the acoustic velocity based on the gas composition or the gas gravity.
I just want to add a note that the surface temperature that you have in the software is the formation temperature, not the ambient temperature.
Right. It's kind of like this. It's like I always say, it's the temperature about 10 or 15 feet below the surface of the ground. So it's a mean annual temperature, close to that.
Okay. Andres is asking, this is related to the round trip travel time below 1.4 seconds, makes the color count disabled. Is there any chances or possibility the data showed in this section could still appear no matter that condition? He uses that for some calculation.
You know, Carrie-Anne ought to show that when she shows an example, and you know the you can scale up or scale down the trace, and you can show and zoom in on TAM to show the first 1.4 seconds over the entire screen. So with the TAM software, we have a lot more flexibility on what's displayed, and I think Carrie-Anne will show that when she shows an example. So let's just hold that question until we look at an acoustic trace, and then we'll talk about the scale of the acoustic signal based on millivolts, and we'll talk about how to zoom in to whatever portion of the trace you want to see, and I think that will help. The main thing that happens when you shoot at fluid level is often the high pressure from the gun creates a hill and hides the first portion of the shot. So if you want to see more clearly the beginning of the shot, then you should use a smaller differential pressure and not have quite as much pressure energy discharged into the well. So you can control that. Also,
Yes.
using that high pass filter may help you see that better because it flattens the curve out.
Right. So Andres, you should be able, using time, to zoom in on the very first portion of the shot, and if you're using a small differential pressure, you should be able to look at much better shape, those first colors in the well. He has another question regarding the C or the color line on this, but that was addressed in the private chat. So I'm going to jump to the next question from Rienzi, and he says, if I'm shooting a static fluid level on a well with no tubing, can I use the average casing length in the average joint length to use for a color count method? And I guess Rienzi is able to see the casing color recesses in that shot.
Right now the software by default uses the average joint length for the tubing to count colors. In the future, we'll be able to enter an average joint length for the surface casing, for the casing, and for the tubing. But right now, the TAM software only uses the average joint length for the tubing. So the answer is yes. Just put in the average joint length, and it will use it if you don't put any tubing in for the casing, or you may have to put tubing average joint length in to get the program to use a casing joint length. So the answer, yes, it'll use it. It's not a problem. Eventually, we'll do it a little different, but right now, if you put casing average joint length, it'll use that with no tubing. If you put tubing and casing in, it'll use the tubing average joint length.
That's correct. And even for the future, we're also considering, aside the casing average joint length, we're even for those people troubleshooting PCP or rod pump wells with rods in it, we're considering to have a field where they can input the rod average joint length so they can shoot a fluid level inside the tube. Okay, next question is from Nidal. He says, when shooting on wells with a kill string, what could I use as the average tubing length? And that's probably related to the previous question. The kill string will be what, 1 or 2 joints. So he will have mainly casing recesses.
Yeah.
If you see them.
So that's a little more complicated question, because when you shoot the fluid level, normally the software ignores the first few colors from the shot. So if your kill string's not very long, then it may see echoes from the kill string, but it may not. Anyway, so it's a little more complicated. So the best answer, and maybe the best answer, is you might want to take a shot or two on that well, and then share that data with Ken Skinner, and he can work with you and help you figure out what to use for the acoustic velocity on the well. Because sometimes it's not a simple answer. This may not be a simple answer because it depends a lot on how long the kill string is, how much energy in the shot, can you see casing colors, there's a lot, is it flush joint, is it kill string flush joint, or is it not? So there's not, I don't really think in this case we can just say a simple answer.
Okay, one more question is from John. He's asking, what is a typical issue or difficulty of accuracy for shallow wells? We use lower differential pressure. Is that enough?
Well, it's better when you have a shallow well and it's not too noisy. Carrie-Anne showed a couple of shallow wells that were noisy because they had PC pumps in them. And for the wells that had PC pumps, they had to use the large volume chamber to get enough energy in the shot to overcome the noise from the PC pump, because they're typically noisy and there's lots of annular gas flow. So if you have a shallow well and it's not noisy and it doesn't have noise from the pump sucking gas out of the casing or pounding fluid, we still normally ignore the first second of data. So if you have a well that's less than 700 foot deep, then we're going to skip counting collars because the liquid level is going to be within the first second of the surface of the beginning of the shot. So you'll have to manually count collars. Usually, if you have, almost always, you have to manually adjust the collar width if you have a shallow well that's less than 700 foot deep. The default collar count won't work. It won't automatically turn on.
But Hugh is asking, is it possible to share a method on particularities of measuring the depth of a tubing hole? And probably that's more related to the dual shot technique and how to find holes in tubing that we have partially discussed in previous sessions.
Yeah. There's a function that Carrie-Anne showed. It's called the depth reference line. And so when you shoot a fluid level and you see an anomalous kick like right here, that down kick, she's showing the depth reference line. You can move that depth reference line right to the down kick, and then you determine the depth. And this is 4,053, and we've noted it was a 4,005. So, but anyway, basically, you can use that depth reference line. And so you look for kicks that don't belong, and you have to say, well, that kick doesn't belong here. There's nothing on the wellbore schematic. And then we would recommend you use your depth reference line to identify the depth.
Okay, Carrie-Anne, that's all I have so far, and I think you can start with some examples you want to show.
Okay, this is the example of that we looked at where the operator had fluid coming out of the hole in the tubing, and so we see a down kick. We see a down kick from that liquid as it's coming out of the hole in the tubing. Then the operator turned the unit off, and now we see an up kick. And so one of the things that you can do in the TAM software, we had a picture of that in this slide, is to overlay the shots. And so under the annotations button, And if I hover on here, you can see it says turn on overlays, trace folding, depth reference line. So if I click on that annotations button, and I can click on previous shots. And so you can see here that we've turned on the previous shot, so we can look at the shot with the down kick overlaid with the shot showing the up kick. And so we can see that they're located at that same depth. I can turn on my depth reference line. All right, so we can get the distance to where that's located. Another thing that you can do that I'm not sure that we've shown in any of the sessions is you can also make notes if you have something in a fluid level shot or dynamometer data. You know, if there's someplace you want to add a note, if you right click in that area and click add note, I can type a little note in here that this was down kick with unit running, something like that. But just a little note here, and then when you click on the report button, then you see the note located on the illustration on the left-hand side, and then you see down here at the bottom the trace notes with the note that was corresponding with that particular. It's almost like a little sticky note, but that's something that comes in really handy to use, and you can make lots of notes on the shot that are also going to be available on your report when you print that out. Anything else on this particular example, Lynn? I think we probably covered that one. We were talking about high fluid levels, so let's take a look at a couple of shots with high fluid levels. If you ever want to go back and reset where the software chose the liquid level, if you click fine tune, go into liquid level and click reset. All right, so if I were to move that liquid level somewhere else, click fine tune, liquid level, and reset, that's going to put it back to the software analysis, right? So where the software initially analyzed and determined where that liquid level marker was located. So we can see here that the software is not even looking prior to that 1.2 second mark. And so we clearly see that there's a liquid level kick here, followed by the repeats of that fluid level. So first thing you want to do is to move your liquid level marker to the correct kick. Now you want to make sure and then look at the collars that were counted. And I think this one did a pretty good job here counting the collars. All right, so as you adjust the collars that were counted, if you look at the acoustic velocity. As I increase and decrease the spacing, you see a difference in the acoustic velocity calculation, right? So if you do need to go in and correct the spacing, just keep note that you're also changing the acoustic velocity. And so that's going to make a difference in your fluid level calculation. Another instance of a high fluid level, this looks a lot more like the example I showed in the presentation. So this is where you have the fluid level kick is right there at the surface, and then the repeats create this sort of funnel, and then it just goes on for as far as the shot ran out. So if you look right here, you'll notice that default software selection at 8.5 seconds. And everything is starred out here. The software is telling me the auto liquid level detection failed, and I need to manually relocate that liquid level marker. So if I move it up here near the beginning of the shot, and I can use some tools to come in here and get close to the beginning of the shot here. So this is where you can scale up and scale down the shot, like Lynn was talking about. There's these scaling buttons, so I can scale it down here. And then I can put my marker on the actual fluid level kick.
Yeah.
Bam, right on it.
Yeah.
All right.
And you know, you can kind of look at the echoes over 1 second, and you can see if you see the repeating signal. You can count those and kind of get an idea that there's 10 echoes per second, and that means the liquid level is about 1/10 of a second from the surface. So you can kind of, in this way, you can kind of see the repeats. And it's a fairly easy way that you can count those and then get an idea it's up high and about where it's at.
All right. Let's look at this multiple kicks gas lift. And all of these data sets that we're looking at are available on our Ask Echometer webpage under the session 14. You've got the PDF bundle, and then right next to that, you've got your TAM example data download. So you're more than welcome to download those data sets, and then you can step through these just to get you some practice going through and analyzing some shots, moving the markers around. So this is a gas lift well, and so here we see the gas lift valves. When I open up the well file, I can come here to lift system, and I see that there are 14 gas lift valves that have been entered on this well. If we looked at the collar count, we see that the collar count was very short. The software wasn't able to identify collars. So let's turn on the downhole marker method, and let me show you how you can step through lining up your gas lift valves as you work your way down. So if I click on this first gas lift valve, and I line that first marker up with that kick, I see the acoustic velocity is 1,130 feet per second. So as I work my way down, the acoustic velocity slightly increases. I'm having to move the marker just a little bit all the way down. And I'll see that it's a steady increase. So if I were to go to the next marker and maybe choose a wrong kick, then I'm going to see a big jump in my acoustic velocity. All right, so that's going to be an indication that I've not selected the correct reflection kick to go along with that marker. But using this method, you can work your way down. If you've got, in this case, there's 14 different gas lift valves to choose from. And you're wanting to get as close as you can to the fluid level. You want to be able to choose the marker that's closest. And some of you, maybe you like being able to turn on that wellbore overlay and you can count down and say, yep, there's my liquid level right there past the 13th valve. But, we're here to show you how to get the most accurate shot and the tools that you have at hand to do that. So this is one way you just work your way down. On some of these other examples that we looked at, here's one with the tubing anchor, the liner, and the gas separator. Again, you've got several kicks here. If I click on the downhole markers, then I have my tubing anchor option. Then I can work my way down. I could say, okay, yep, there's my liner kick. Maybe that needs to be corrected just a little bit. Remember, we're lining it up on the knee of the kick, that point where that downward motion starts. All right, so then I say, okay, well, I've got a kick right here. It's the top of the gas separator. And then here, the next is my liquid level kick. All right, so then we're able to, we can turn on our depth reference line. So if you wanted to further verify, you've got a certain amount of distance from that liner top to the liquid level, and then from the liquid level to that up kick. That's going to help you verify that that up kick is the liner top as that pressure wave is coming back out of the wellbore. So just because you have a shot with a lot of kicks, multiple kicks, get that wellbore schematic. You can enter that information into the well file. If you're not sure what information to enter, one thing you can do is just go down and look for significant changes in cross-sectional area. Look for items like the tubing anchor, like a liner, gas lift valves, and mandrels. I'm sorry, Lynn?
This is a good well to fold the trace at the liquid level.
Okay, so if I click on the annotations button, let me turn off this line here. So when I click fold trace, it's going to fold the trace. Oh, I moved that liquid level, didn't I? It's going to fold the trace at that liquid level. All right, so we see the down kick from the liner and the up kick as that pressure is traveling back out of the liner. We see the kick off the tubing anchor. Any questions so far? All right. Here is the casing weight change. So in this well, let's see if we turn on the wellbore overlay, you can make it a little bit darker here. All right, so we see this down kick right here, but we don't see anything in the wellbore. So we can take a look at the wellbore schematic. I think it's written in the well file here. All right, so at 5,913 feet, the wellbore goes from 26-pound casing to 38-pound casing. All right, so 5913 from 26 to 38. Y'all gonna help me remember that. So if we go into the well file and go into mechanical wellbore, so at 5,913 feet, right? And this was 9,000. It goes from 26-pound casing to 38-pound casing, correct? Nobody does. All right. So that created a little ledge there. So now we see a difference in that cross-sectional area just from that casing weight change. So now we see a downward kick. So the collar count on this particular well only made it about halfway down, but we have this casing weight change. So we can actually use that casing weight change as our downhole marker and get a little bit more accurate fluid level shot. All right, so, but you can see how easy it is. If you have something on your wellbore schematic that you want to go in and enter, just click on the edit button so you can enter in that information. So that you let the software know what type of artificial lift system it is, so if it's rod pump or if it's an ESP or gas lift, plunger lift. And so the software lets you know what information it's looking for. So when you're entering in the additional information, you're going to see that show up in that illustration. So that's what you're going to see on that wellbore overlay when you turn that on.
Carrie-Anne, this example, this data was imported from TWM, and so this is a description that was used for the downhole marker method inside TWM, and it's shown as a tubular marker. So if you go back and see, there's two markers. One's that you type that one in, and the next one is called a tubular marker. So that's an option if there's not an easy way like changing the casing weight. You can also go in manually on the second tab from the bottom and add in the edit mode and add that specific marker. So there's a
right there. Okay.
Yeah, so that would be like you would type one in that you wanted some specific wording to show up on your analysis.
All right. Do you see anything else?
One of the things we talked about, this is a good one too, but one of the things we talked about was the looking at 1.4 seconds. So the well that has a casing weight change is a fairly centered acoustic trace, and you can move the zoom into the first 1.4 seconds, and then scale it down, and look at the background noise. That was a question we had earlier. So
Okay.
So go to this shot, and then pull that over the narrow the window up to like 1.5 seconds. You know, with your right there. So that's more. Go to 1.5. Make it a little tiny. There you go. And now scale it down with a minus, and so you can see the collar echo. So if you put, you're going to do it a different way. I'm sorry.
No, I was going to show them how you can zoom in. So if you wanted to select a region, right?
Mm-hmm.
And you can scale that down.
Yeah. But you know, the question was about, I like to look at my collars in the first 1.4 seconds. Well, with the TAM software, you're able to zoom into a little tiny section of the wellbore and look at the collars. So you have a lot more functionality here with the TAM software than you had with the TWM software, because you can zoom the window in and look really close. So that really increases. So if you've identified that the collar echoes in the first 1.5 seconds of your shot are important to look at, TAM makes that easy to do.
So these two shots show the difference in implosion and explosion. The first shot was a compact gas gun implosion shot. So there were 205 pounds of pressure on this well. So we shot 205 pounds of pressure to get this particular shot. And then using the compact gas gun, we performed an explosion shot. And so there's 400 pounds of pressure in the gun, creating that 200 psi pressure differential. So we can go in and overlay these. If I click annotations, previous shots, I can turn on that shot, and then we can spread those apart. Another thing to remember, if you're overlaying shots, you can overlay them by depth or by time. And essentially, if you have the shots analyzed correctly, they should overlay the same either way. But sometimes you're needing to be able to overlay shots, you know, like if you're moving the liquid level, you need to try to find where that liquid level's at after you've shut the well in for a period of time, or you've turned off the pumping unit and you've got the rate of fill up working for you. So if you overlay shots by depth, it's going to use the analysis that you have done on the shot. If you overlay the shot by time, then it's going to overlay them by time. And so sometimes overlaying shots by time is going to make it easier for you to line things up. So that's where you're going to see the stationary things in the wellbore are going to always follow at the same time. And that's going to help you see what's different, to see what's changed as you're overlaying those shots. Any other comments on that?
Just a question. I think there is a little confusion on the liquid level or acoustic velocity method to determine the liquid level depth. And Nidal is asking, is the liquid level still accurate here, even though the color count radio is less than 70% by using the downhole marker? And he's mixing the methods.
Okay, so the question was, is the liquid level still accurate even though the collar count ratio is less than 70% by using the downhole marker method? If I'm understanding the question correctly, when we're looking at the depth to, or the distance to the liquid level from the beginning of the shot, the collar count and the downhole marker are two separate methods to analyze the shot, right, to determine the depth. And so the collar count is determined by the software and how many collars it can actually count. And so we see here that the collar count is just past about 50% of the way down to the liquid level. The downhole marker, if we were to use this casing weight change as a downhole marker, it gets us a little bit closer. So it gets us closer to about 70%. So it does improve the accuracy a little bit. You know, and this is just one of the examples that we happen to have here showing where the collar count is not as deep as the downhole marker. And again, the accuracy is also going to depend on, you know, with that collar count method, you want to make sure that you've got your average joint length in correctly. With the downhole marker method, you're essentially using the number directly from your wellbore schematic. Please let me know if that answered your question.
Can I make a couple comments?
Yeah.
On this well, if you look at the lower right-hand corner, you can see that the casing pressure is not building up. And so when the casing pressure doesn't build up, that means there's no annular gas flow. And that can mean the gas can segregate. And in this well, this down kick that Carrie-Anne has her mouse close to is due to the casing weight change. But in some wells, that don't have gas flow, you might have a down kick, and that could be due to the butane propane has settled to the bottom of the well, and the methane has floated to the top. And so you can even see a kick at the interface between the two gases. So that can happen, and it'll look just like this. But what happens though is that there's also something that changes in this well. Not only the gas composition is changing, but the temperature changes, and the temperature increases acoustic velocity. So when you look at the collar spacing may change so much based on the temperature that the software automatic collar count method stops because the collars don't fit in the window that we've selected. So there's a couple things that can be going on counting deep. Is that either the well can be getting really hot, acoustic velocity can be changing. If there's no gas flow, the gas composition can be changing, and the spacing of the collars can be a lot different because the gas near the surface of the well and the gas at the bottom of the well can be different. So there's several things that can cause us not to count deep into the well, but often it's just noise. In this case, it could be it doesn't appear to be noise. The noise is low, background noise is small, but there's a reason it stopped, and probably it stopped because of the big kick at the casing weight change, and then the automatic method failed because of that big kick. All right.
I was just reading the chat, and it looks like there's another question that came in. Is there any chance to identify a washout on the pipeline and differentiate it from a liquid level?
Well, that would behave completely different. Whole kick compared to a liquid level kick. Please go ahead.
Yes, absolutely. So if you've got a hole in the tubing or the casing, there's going to be an increase in area. So the behavior of the reflection kick, it will respond as an upward kick to that increase in area. A fluid level, the liquid level kick, when it hits an obstruction or something taking up space, then we see a downward kick. So yes, there would be a definite difference in an up kick from the hole and then a down kick from the liquid level. Let's see, here we have all right, so here we see an up kick right here. This is an up kick from a hole in the tubing. And we see our liquid level is down here a ways. And so there's quite a bit of energy coming off of that shot when it hits that hole in the tubing. So we see a pretty big up kick here. It doesn't say how big that hole was. All right, but this is what you would expect to see. And if you're shooting down the casing and you see an up kick, then one thing you can do is shoot down the tubing. And that if you see an up kick in the tubing and the casing at that same location, then you know that hole is in the tubing. If you shoot down the tubing and there's no up kick, then you know it's a problem with the casing.
This well has a casing shot too, so there's casing shots and
yeah, I
shots.
think they're overlaid.
Yeah.
All right, so here we have this black trace here. Shows the hole on the casing shot, and then this blue is the hole from the tubing shot. All right, any other questions or comments?
I'll make a real quick comment on this well. You know, in a gas well, there's no pump. And so usually on a well with a pump, the liquid level is above the pump. But on a gas well, when the casing is closed in for plunger lift, then the gas accumulates in the casing, and pushes a liquid level down to the end of the tubing. So a troubleshooting technique on a gas well is to always shoot the casing first and see if the liquid level is at the end of the tubing. It should be. If it's not, then you need to shoot down the tubing and investigate what's going on with the well. All right, thank you.
We sure appreciate your time today, and thank you for your questions, and I thank everyone for their responses and inputs. And we will see you next Wednesday. Thank you so much. You have a great weekend.
Thank you.